Today I'll be discussing the Diels Alder reaction, and this video will cover a wide variety of possibilities and can serve as a comprehensive guide to what you'll see in class. But because of this, the video will be longer than normal, and to help with that, I've included timestamps in the description for the variety of topics essential to this reaction. But please excuse my goofy intro art, and let's get on with reaction. Diels Alder is a concerted mechanism, so all the new bonds are forming simultaneously. And this converts a S-cis diene and a dienophile with heat into a cyclohexene. Now I presented the mechanism as having the electron pushing arrows in a counterclockwise fashion, but it could have just as easily been in a clockwise fashion. So this foundational and simplest form of the Diels Alder reaction is between a 1,3-butadiene, so a conjugated diene with 4 pi electrons, and an ethene, an alkene with 2 pi electrons, with heat, to yield a cyclohexene with 2 pi electrons. However, this reaction is low yield. It becomes higher yield with electron-rich diene and electron-deficient dienophile. How does this occur? Via electron donating and electron withdrawing groups. But first, I think it's necessary to discuss the conformation required of our diene for this reaction to occur in the first place. Presented above is an S-trans diene. However, we need an S-cis or the possibility of an S-cis diene for our Diels Alder reaction to occur. Thankfully, if you remember, we have free rotation around our single or sigma bond. But this takes some energy, because the S-cis conformation has more steric hindrance. Luckily, the Diels Alder reaction uses heat, and this energy is no problem as long as free rotation is allowed. So a possible Diels Alder reaction that you may see might have the diene in an S-trans state, but this is fine as long as you get that free rotation. Well, what's an example where we wouldn't get free rotation? Here's a possibility. Because the diene is in an S-trans here, but single bond rotation is restricted in cyclic compounds, the ring structure constrains the rotation and thus no reaction. As I previously mentioned, the simplest Diels Alder reaction is a 1,3-butadiene and an ethene with heat, and is relatively low yield compared to an electron-rich diene and an electron-poor dienophile. These descriptions are achieved by substituents attached to our quote-unquote foundational diene and dienophile to manipulate the electron density via resonance or induction. An alkyl group such as this methyl donates its electrons by induction. While, for example, if this was 1-methoxy 1,3-butadiene, that oxygen has a lone pair that's donating by resonance. Moving down to the dienophiles, we want electron withdrawing groups. Here are the common groups that withdraw by resonance, and one that withdraws by induction. As a note, NO2 is one of the strongest deactivators, and it also has an inductive effect. I will be using a few of these common dienes and dienophiles in the example problems, and how they do their job will become more clear. We will be working one by one through these 3 scenarios to cover most of the rules of the Diels Alder reaction, followed by an on-your-own problem. There is also one more scenario presented following all of this that takes that knowledge learned and expands it, followed by another on-your-own problem on that topic. First, the relative stereochemistry of the diene and dienophile must be maintained in the final product. So if our groups are trans across our alkene, the dienophile, as presented here, they must stay trans in the final cyclohexene. If they were cis, they would have to stay cis in the final cyclohexene. As I have this written, I neglected to also write plus enantiomer, which is important to note because we are discussing relative stereochemistry but not absolute. So I should have written plus enantiomer, so don't let that confuse you. Like I said, this rule applies for the diene as well. These methyl groups on the 1 and 4 position are both considered to be pointing outside, or trans with that sigma bond of the diene. They will maintain this in the final product. And no enantiomer needed here because this is a meso molecule. So number 1 here is going to have plus enantiomer, like I said. But moving on to number 2, we will be looking at how substituents will guide regioselectivity of our reaction. With the previous example, we saw a dienophile that had the same groups equally but oppositely withdrawing electrons. Therefore, there was no differential distribution of charges across the dienophile. Regioselectivity becomes a concern when our diene and dienophile are asymmetrically substituted. Asymmetrically substituted dienes and dienophiles result in an asymmetrical distribution of charges, which is evident by looking at the second best resonance structure. And the asymmetrical distribution of charges will cause the diene and dienophile to line up in a specific way. The diene and dienophile above illustrate this concept. For example, the dienophile has one carbon of the alkene that is more populated with electron withdrawing groups. Now let's look at the charge distribution on the diene by looking at the second best resonance structure. The first step to determining the second best resonance structure of our diene is to look at the possible resonance structures. Here I will separate out the possible resonance structures into two brackets, just for simplicity's sake and to ensure there's no confusion. One possibility is the lone pair from our oxygen donates its electrons. Here all of our atoms will have full octets. Another resonance structure possibility involves the double bonds moving. For example, like this. Now this can happen in the opposite direction obviously, though either way, every atom will not have a full octet due to that positive charge. One carbon will have 6 electrons always. So I won't draw it out, and it's not going to be our second best resonance structure either way. This is our second best resonance structure for the diene. Now let's take a closer look at the dienophile. How is the trifluoromethyl electron withdrawing? Those 3 fluorines on one carbon are very electronegative and pulling electrons, placing a partial positive charge on the carbon. So, when looking at the second best resonance structure, it is the one where this molecule is in a state that there is not a positive charge at the adjacent carbon. It's unfavorable to put a positive charge next to this partial positive. This molecule here is our second best resonance structure for our dienophile. Now the final step is to line up the opposite charges of the second best resonance structures for the diene and dienophile. We combine the most nucleophilic portion of the diene and the most electrophilic portion of the dienophile. This would require we flip one of our molecules. Here, let's flip the dienophile. Now this tactic I just covered is simply for determining the regioselectivity of our major product. Though, when writing out the mechanism, this process would not be included and the electron pushing arrows would occur using the best resonance structures or our original molecules without this charge distribution visualized. Moving forward, we get to the most complicated concept. Recall that a dienophile with trans or cis orientation about the double bond will retain that relationship in the final product. Also recall that this too applies to our diene. Now how are these relative stereochemistries formed in relation to each other? When groups on both our diene and dienophile go from sp2 to sp3, in the transition state there are 2 possible orientations that result in specific stereochemistry rules. In general, the rule we follow is for the endo product, and this is our major product. First, we must find the second best resonance structures for our diene and dienophile because they are both asymmetrically substituted and thus regioselectivity is a factor in the final product. Try this one on your own. For our diene, both possibilities result in a carbon with 6 electrons. However, that positive charge is more comfortable on a secondary position rather than a primary position. The dienophile has our strongest electron withdrawing group, the nitro group, withdrawing by induction and resonance. We want that carbocation as far away from the positive of the nitro group as possible. Also, the oxygen atoms have a negative formal charge. Now that we have the regioselectivity down of our end product, what's the stereochemistry? The endo rule is in general the major product for Diels Alder's reactions. The best way to remember it is, if our group is cis to the sigma bond of our diene, then it will be trans to the bulky side of our dienophile. Now if there were to be 2 electron withdrawing groups on one carbon of our dienophile, then there would be no bulkier side. If there were 1 electron withdrawing group on both carbons of our dienophile, but these groups were trans to each other, there would be no bulkier side. But because presented above, there is either 1 electron withdrawing group on each carbon and they are cis, there's going to be a bulkier side of the dienophile. And because there's only 1 electron withdrawing group on our dienophile on this other molecule, there's going to be a bulkier side. Here is our sigma bond. groups on our diene, like this methyl group, that are cis to our sigma bond, aka form a cis alkene with their sigma bond, these groups are also called inside groups. They will be trans to the bulky side of our dienophile. Here is that bulkier side of our dienophile. So that methyl will be on one face of our six-membered ring final product, while those trifluoromethyls will have the trans stereochemistry. For example, if that methyl is coming at us, then those trifluoromethyls will be both pointing away from us. If you keep the rule cis to sigma, trans to bulky in mind, no matter how the orientation of our diene and dienophile is presented, you will get the correct product, as long as you adhere to the previous rules as well. And remember, these rules say nothing about absolute configuration, such as a preset determination of R or S. These are rules for relative stereochemistry between groups. So as I said, for the endo rule of cis to sigma, trans to bulky, the exact opposite also applies. So trans to sigma, cis to bulky. Here, our group on our diene forms a trans alkene with the sigma bond, or you may see it being called an outside group. And here is the bulkier side of our dienophile. So that methyl will be on one face of our final product, the six-membered ring, and that trifluoromethyl group will be on the same side. For example, that methyl is pointing towards us, and that trifluoromethyl group is pointing towards us as well. As I mentioned, this is the endo rule for the endo products of Diels Alder. There's also the exo rule, which would correspond to cis to sigma, cis to bulky, and trans to sigma, trans to bulky. However, the majority of the time, the endo product is a favored product. So coming back to our original practice problem in the top left corner, we have oriented these molecules according to the rules governing regioselectivity, and have found the skeleton of our final product, though we now need to implement the endo rule that we just discussed. The methyl group present on our diene is trans with our sigma bond. Thus, cis to sigma, trans to bulky, and trans to bulky, cis to sigma, here is the bulkier side of our dienophile. Our groups will therefore be on the same side of our molecule. Try this one on your own. Regioselectivity is unimportant here. Our alkyl groups are equally directing, so our diene can be thought of as symmetrical in regards to electron donating. Same can be said with the dienophile. These two electron withdrawing groups can be thought of as equally in regards to Diels Alder. They are both strong deactivators. What we need to be aware of is relative stereochemistry because we have a bulkier side of the dienophile. As we just covered stereochemistry of Diels Alders, it seems like a good time to introduce an idea. Cyclic dienes are very reactive in a Diels Alder reaction. If they are in a S-cis conformation, they are locked this way. So this reaction looks complicated, but as you can see, if we block out this newly introduced bit, we could see our more recognizable diene of our Diels Alder's reaction we have been discussing. And the mechanism proceeds through the same steps as we've been discussing. And the same rules apply here for stereochemistry that we recently discussed. Cis to sigma, trans to bulky. What's cis to sigma here? Our bridgehead. Here, the bridgehead is represented as coming at us, with the peak being the CH2. We can also look at it through a side view, and these are both acceptable answers on a test. We can also have cyclic dienophiles. Try this problem on your own.